Hi, my name is Graham Wilson. I'm from the University of Glasgow, and this paper is part of our work looking at virtual reality interaction in constrained transport seating. The advent of standalone headsets means that VR can now be used on the go, including on various forms of transport. And the move towards autonomous vehicles also means that drivers are becoming passengers and having more time to spend on entertainment or productivity. VR also offers several advantages over devices like phones, tablets, or laptops, including escapism from others nearby or a boring commute, large configurable workspaces for productivity, with displays placed in comfortable and ergonomic positions compared to small laptop screens, or just being immersed in engaging media or games. There are now thousands of commercial VR experiences available through storefronts like Meta and Steam, predominantly games. And most of these involve large, fast or uncontrolled movements like swinging arms, firing guns, throwing objects or social gestures. And therefore experiences are categorized by the amount of open space that they require, such as 1 by 1 meter for seated or standing spaces, or 2 by 2 meters for room scale spaces. But the reality of public transport is that seating is heavily constrained. There are seats in front of you, walls and windows to the side, tables, armrests, and other passengers. So train seats might have only 60 by 80 centimeters of space, while economy airline seats have as little as 45 by 55 centimeters. To put that into perspective, here we have a room scale space, then a standing VR space, but then we have the space available on a train and the space available on a plane seat. So it's not really possible to use commercial VR experiences on transport. Therefore, our research aimed to find out if we can equalize the interaction capabilities of at-home and on-transport users. And essentially, can we provide access to commercial experiences or interactions from constrained interaction spaces? Using techniques that are application agnostic, so they are not designed specifically for the application or vice versa, and that support the most common input actions in commercial apps. But importantly, while keeping users within the constrained interaction boundary. Our research process was first to identify the most common VR movement inputs in the top 25 commercial experiences on the Meta and Steam stores. I won't cover this process in the talk, but you can learn more about it in the paper. We then designed 3 gamified tasks that involved these common movements and identified and adapted 3 effective at-a-distance interaction techniques from the literature to be able to play each of the 3 games. We then tested how each technique supports each task or commercial input in a constrained interaction space of 50 by 50 centimeters. So, having identified the most common movement inputs, we used them to create 3 gamified tasks. All 3 used an interactive virtual space of 1 by 1 meter, the same as common seated standing experiences, so all elements could be interacted with within 1 by 1 meter of virtual space. And we used a constrained interaction space of 50 by 50 centimeters, similar to airline economy seats. This resulted in an interaction volume something like this, and all constrained interactions were done sat down in chairs to represent transport seating. The 3 tasks were selection and manipulation, sword swinging, and shooting, and they were designed to elicit realistic behaviour and movements which could risk violating the boundaries if they weren't properly controlled. In the selection and manipulation task, players had to grab a dog biscuit and feed it to a virtual dog. They had to place it accurately in the mouth, as well as match the rotation of the biscuit to the angle of the dog's mouth. And points were only earned if it was placed correctly. The sword swinging task had players defeating invaders by attacking with a sword, either swinging it from top to bottom for enemies with a shield, or side to side for ones with a helmet. And points were gained by swinging in the correct direction. In the shooting task, players shot moving robot drones with a laser gun, while the drones moved and fired back at the player. More points were gained by shooting the drones quickly. To play the games from a constrained space, we adapted 3 at-a-distance interaction techniques from the literature. The techniques were a 2 times linear gain, or amplification, a head pose variant of gaze-supported remote hand, and alpha cursor. We compared these constrained sat-down techniques to a traditional at-home condition with standing up, one-to-one movement. All techniques were adapted from the originals as they were designed for either only target selection or selection and manipulation. In the linear gain technique, the virtual hand, shown here in white, moves twice as far from the body as the real hand, which is shown here in grey but was not visible in the real task. In our head pose variant of gaze-supported remote hand, a targeting circle in the centre of the view was used to indicate what object the player wanted to interact with by facing the head at it. They then used a button on the controller to teleport the virtual hand to that object. The real hand could then be used to move the virtual hand from this new position. In Alpha Cursor, a red line is shown emanating from the controller, and the player can use the joystick to move the virtual hand along the line, with the speed based on how far the joystick is pressed. And we compared these techniques to a traditional at-home setup, where the user was standing and movement was tracked one-to-one within the full 1x1 meter virtual space. So we'll be able to determine how closely each technique matches outcomes from the current gold standard. We ran a within-subject experiment with 16 participants who completed all 3 gamified tasks in a random order within all 4 techniques, which were counterbalanced. They were told that the aim of the study was to remain within the constrained boundary as much as possible, which was visualized as a black grid that became more visible as the real hand got closer. They were also to score as many points as they could by completing tasks quickly but accurately. We measured different forms of task performance, including accuracy, trial time, and the number of trials not completed in time. We measured the number of times the interacting hand violated a boundary, as well as the total amount of arm movement. And we also gathered subjective views on presence, embodiment, comfort, safety on transport, and workload. I won't go into the detail on the results, they can be found in the paper. I'll just cover the general high-level findings. In terms of evaluating and comparing the techniques, linear gain led to the best task performance of the constrained techniques and was not significantly different from the at-home condition. It also had comparable, so not significantly different presence and embodiment to at-home. However, it led to the highest number of boundary violations as well as the most arm movement of the constrained techniques. In contrast, Alpha Cursor led to good performance, though not as good as linear gain, as well as the lowest number of boundary violations, so it kept players within the bounds the best. However, it led to lower presence and embodiment than the other techniques because of the mismatch between the real and virtual movement of the hand. Finally, our head pose version of gaze-supported remote hand led to poorer performance and was more difficult to use than the other techniques due to the amount of head movement. From the results, we produced a number of guidelines for the use or study of interactions with commercial experiences in constrained spaces. Firstly, our adapted at-a-distance techniques among them supported all the common movement inputs from commercial experiences. Linear gain best supports selection and manipulation style interactions. All the techniques equally support arm swinging style inputs, and both linear gain and Alpha Cursor support shooting or aiming interactions. Our general guidelines include linear gain is best for equalizing at-home and constrained interaction. However, we need to identify ways to reduce the number of boundary violations or arm movement to ensure it's fully usable. In contrast, Alpha Cursor best keeps users within the constrained play boundaries and requires the least amount of movement, which is potentially important because users are not aware of the extent of their boundary violations or the amount of arm movement. And finally, we found that technique influences subjective immersive experience in presence and embodiment, so we recommend that research proposing at-a-distance or constrained interactions considers and measures the effect of the novel techniques on these important phenomena.